my name is Sagrika Srinivasan, and today I'll be presenting my projectile motion lab for Physics 2211. In this experiment, I analyzed the trajectory of an object and compared experimental data with computational models. This is the general overview of today's video. We're going to start off with our introduction, then go to our models, then experiment, then coding, then discussion, and then conclusions. The purpose of this lab was twofold. I wanted to initially model projectile motion using Newton's second law, one model that would only use gravity, and a second model that would include both gravity and air drag. The key question here is, does drag actually affect the motion of a ball? Because we often ignore air resistance in introductory physics problems, but is it significant for a real-world object? So here are some physics concepts. The lab relies on three main ideas. First, Newton's second law, that F is equal to ma, or the net force equals to the change in momentum over time. Second is the gravitational force, which is always acting downward with a magnitude of mg. And third is the drag force. F drag equals negative b times v squared times v hat. Here b is the drag coefficient. And the key thing to remember is that drag always opposes motion and its magnitude is proportional to the square of the speed. So this is the experimental procedure. First, we had to record the crumpled ball's tracked motion. Then I uploaded the video into Tracker and used software to track the ball's movement. And after that, I used GlowScript starter code to measure the predicted values, and I put both of the values into Excel and compared them. This is the projectile motion video. So generally here you can see the experimental setup. We have an object, which is a crumpled up paper ball, the surrounding air resistance. The real outcome is measured in Tracker, and the predicted position is in GlowScript. So this is my actual versus predicted. Tracker is modeling what actually happened. And then both without drag and with drag are my predicted graphs from GlowScript. As you can see, the one that is with drag has less resistance, more resistance than the one without drag. This is the GlowScript predicted video. And this is the code. So essentially here, at the top, I'm defining my initial conditions, which is the ball's mass, initial position, and initial velocity. In the main loop, I'm calculating the net force, and for the gravity-only case, it's simply negative mg in the y direction. For the drag case, I first calculate the speed as the magnitude of velocity, then compute the drag force as negative b times speed squared times the unit vector of velocity. I then update the momentum using p new. The new position is equal to the old position plus f net. And the loop continues plotting the trajectory point by point until the ball hits the ground. There were unfortunately definitely a lot of sources of error in this experiment. We had the uneven ball surface, which could have led to unexpected air resistance, possibly the wrong drag proportionate constant, because I did get some negative values. There was an unclear start in the way that we recorded the video, so there could have been a point where there was a force being applied on a ball when we assumed that there were no other forces, and the slightly shaky video might have affected the calibration. To answer the what if and what does it mean questions, if the ball was thrown straight up, it would hit the ground a little bit later. This is because if the absolute magnitude of the speed is conserved in the y direction, that means the ball is going to actually travel to a higher height. And since the time to fall is defined as the square root of 2 times the height over g, it would hit the ground a little bit later. And for the what does it mean? Yes, in the case that we did not account for drag, that is an example of terminal velocity because there isn't the force of air resistance. Thank you so much.